consider a game where I keep flipping a coin, and every time it comes out heads, I get $1. Every time it comes out tails, I lose $1. You might get some payoff that looks like this, where I start out with no money, I get a heads, I get a tails, tails, heads, 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 tails, and up there. And so if we let S be the value of my winnings and R be the change, so RI will be plus or minus 1 randomly. That's the coin flip. And S will be the sum of the R's. So it'll be sum of Rj, j equals 1 to n, or 1 to I. All right, so that's our little game. This gives a random walk for my my winnings. And you can see it, it goes up and down. It's never going to get infinite. I only play a finite number of rounds. So what else can I say about it? Another important property is the Markov property. This means that the coin has no memory. If I keep playing the game after 100 rounds, the game hasn't changed. Whatever happened in the past 100 rounds doesn't affect what happens in the future. So no memory. It's the Markov property. There's also a martingale property. So the martingale property says that the expected winnings in the future from any point are exactly what I have now. So the expected winnings in the future are always what I have now. You can write that mathematically. So the expected value of S of j given S of I, where I is less than j, equals S of I. So j is the future, I is the present. Whatever I have now, I expect every time in the future to have the same value of winnings I have now. That's related to it being a fair game. All right, so these are two of the properties that this simple random walk has. Now we want to make it continuous to give a continuous random walk. So that's called Brownian motion. And in order to make it continuous, we have to start subdividing this random walk into more and more trials in smaller and smaller time scales. So let's instead divide into n steps over time t. All right, and now instead of plus or minus 1, we're going to say R of I equals plus or minus t over n. So we're scaling our bets every time, and we still have the SIs are the sums of the RIs. All right, so now we can play this game. What are some facts about this game? Well, the expected value of SI, what's this going to be? We still have plus or minus randomly by the coin flip, so the expected value of our winnings at every time is going to be 0. What about the expected value of RI? This is randomly plus or minus the same value, so this is going to be 0. What about Ri squared? The expected value of Ri squared, squaring this always gives t over n. And finally, the expected value of Ri, Rj equals, if I is not equal to j, this will be the product. So if I is not equal to j, they're independent, so it'll be the product, and these are both just 0, so that'll be 0. Another interesting thing to calculate is the expectation of SI squared. What's that going to be? That's going to be the expected value of each of these things. So I'm just going to write out the definition of the SI. And now multiplying this out, you're going to get a whole bunch of terms. And the interesting ones are the R1, R times R1 will give R1 squared, plus you'll have a bunch of terms like R1, R2, plus a whole bunch of stuff. And you'll end up with Ri minus 1. I'm just multiplying all these out. And the only terms that matter are the squared terms. So the 1, 2, the 2, 3, the 3 1s, all these middle terms will cancel out. And we're left with, and that's because of this property here, that if I is not equal to j, the expected value is 0. And so we'll get R1 squared plus R2 squared. So we're left with the squared terms here. And each one will be t over n. We have I of them, so we'll have I times t over n. And then in particular, e of Sn squared will be t. So that's interesting. Now for the Brownian motion part, we want to take the limit as n goes to infinity. And what's going to happen? First of all, we're going to have, and we're going to, so we're going to take the limit as n goes to infinity, and we're going to call it the resulting process x of t. And this will be Brownian motion. This is the continuous limit of continually dividing this game we're playing with the random walk into more and more steps until it's a continuous process. And now some of the facts about this, the expected value of x of t will be 0. So this is just, I'm taking the same facts we did up here and taking them to the limit. They don't change. So the expected value of the Brownian motion will be 0. The expected value of x of t squared, so that's just this one here, will end up being t. And then there's some other properties which I'm not going to prove, but you can prove. You have things like it remains finite. And part of the intuition behind that is if you look at these two results here, so here and here, this is a hint that it stays finite. And why is it a hint? Well, if you think, what's the expected value of how far the walk goes away from the origin, it'll be related to the square root of this number here. So this is the variance, and you can think that how far away you get from the origin is related to this number. And because this is not, going to infinity or something, that means that the whole process is going to stay bounded and finite. So what are the properties? It's actually continuous. And then we have our other ones. So we have Markov. So there's no memory still. So in the limit, as n goes to infinity, it still has no memory of the past. And we can write that a bit more mathematically as the distribution of x of t given some tau less than t only depends on x of tau. This just means that if we're at the present tau looking into the future t, our expectations about what's going to happen in the future at t only depends on what's happened right now. This is very similar to our Markov property up here, where we just said there's no memory of the coin flip. All the coin flips in the past don't affect the coin flips in the future. This is just the continuous version of that property. And then we have a martingale property. And the martingale property, remember, said the expected value in the future is just what we have now, but now we have continuous, so we have to be a little bit more careful. And so the expected value of the future given the present, where the present is less than the future, is equal to exactly the present. So here's the future given the present is equal to the present. And that's the martingale property. And there's another interesting property about the Brownian motion, and that's normality. And that says that for any time tau less than t, that x of t minus x of tau is normal. And in particular, it's normal with a mean of 0 and a standard deviation of root t minus tau. And so that's very neat. This means that we can simulate a Brownian motion using discrete time steps. So we can write a program that generates normal numbers, and because of this property here, we can have some discrete time step and have a bunch of samples, and then actually generate some random walk simulation. So there it is. These are the properties of Brownian motion.